Teddy, ask Fluffy Bunny if she wants more tea.
He's good.
You're not allowed phones at tea parties. Ask Fluffy Bunny if she wants more tea.
Okay, oh, hi there! How are you? Didn't hear you come in. Oh, I guess we have to take a break from the tea party for now. Well, we've done a lot of work with permutations so far in this course, and we actually started with stuffed animals, so maybe it's kind of nice that we're back to stuffed animals. Let's review this concept of, well, 4 stuffed animals can be lined up 4 times 3 times 2 times 1 different ways, or 4 factorial ways. How about how many 4 stuffed animal lineups are there if you have 10 stuffed animals to choose from? So we've got these other 6 stuffed animals here, which can also be part of the lineup. So I can make new lineups, of course, by trading stuffed animals or by switching the order of stuffed animals. And we did that as well. And we got, you see that okay? We got 10 times 9 times 8 times 7 different possible stuffed animal lineups, which is the same as talking about a permutation of length 4 made up of 10 objects. And a shortcut to doing 10 times 9 times 8 times 7, because that looks like 10 factorial, a shortcut is to take 10 factorial and divide it by 6 factorial. So you eliminate the times 6 times 5 times 4 and so on. And you get 5,040 different stuffed animal lineups. Now, a more interesting question might be, we had 4 animals that we chose for a tea party. There are 10 animals total. So another question might be, how many possible animals could we have, or groups of stuffed animals could we have for our tea party? We don't actually care about the order. We just care whether the animals are at the tea party or whether they are not. So another example might be that, like, this is no longer a new tea party. This is no longer a new tea party. They don't have, like, an order associated with them. In order to make a new tea party, I have to replace Tigger with Muffin, for example. Now that's a new tea party. So let's look at that question now. That's actually called a combination in math. How many combinations can we come up with? How many ways can we choose 4 stuffed animals out of 10? Well, take a look here. We've already said that the number of ways to line up 4 stuffed animals out of 10 is 5,040. So imagine I've got my 4 stuffed animals here. How many ways can I arrange them? 4 factorial. There are 4 factorial arrangements of these 4 stuffed animals. So the 5,040 number we came up with, that includes all the arrangements of the 4 animals. We don't want arrangements though, so we actually need to take 5,040 and divide by all the possible arrangements of the stuffed animals. Now 4 factorial is 24. So our actual answer is 5,040 divided by 24, or 210 different ways to select 4 stuffed animals out of 10 total. And we arrived at that by looking at the permutations of length 4, the different lineups you could have of 4 stuffed animals, and then realizing that for every single one of those lineups, we've counted all the ways you can arrange them. And since we don't want those arrangements anymore, we divide by those 24 possible ways. There's 24 ways to arrange those animals. Okay, let's look at some more examples and get into this topic a little bit more, shall we? So let's take a look at another example that's very similar to the stuffed animal example of how many ways can you choose 4 out of 10 stuffed animals. Of course, 210 was the answer to that. Imagine you've got 5 students, and I've given them 5 different names, and they're going to complete a school project together. 3 of the students of the 5 will then be chosen to present the project to the class. How many possible ways are there to choose the 3 people who will be the presenters? So when I see this, I kind of think of, since we have 5 students and we have 3 that will be presenters, it's kind of like we're saying, look, you've got 5 people, and how many ways can you choose 3? Now, it's not that many. You could actually possibly write them all out, which is what makes this a good example to start with. So at first we might start this by saying, okay, there are 3 presenters. I have 5 choices for presenter number 1, 4 choices for presenter number 3, and 3 choices for presenter number 3. So I could say 5 times 4 times 3, which is equal to 60. That's also the same as the number of permutations of length 3 from 5 different people. Now, consider those 60 as our answer. Okay, it's not actually the answer. Let me just explain why. So imagine we pick, say, Anna, Sue, and Jim. I'm just going to say A, S, and J. Suppose that's one of our presenters. Well, according to this, the 60 possibilities, this is another possibility. Okay, J, S, and A. Okay, Jim, Sue, and Anna. I'm going to stop calling them by names and just use letters. And another possibility is S, A, J. However, in this question, we don't care about presenter 1, presenter 2, presenter 3. We think that these should all be the same group of presenters. This is the same group of 3 chosen each time. So the 60 counts these as different permutations, these 3. So we've overcounted the number of groups there actually are. In fact, I can go ahead and write, it's not even that hard, to write all the possible ways I could arrange A, S, and J. I've got 3 of them. Here's another one. There's another one. And finally, the last one. There are 6 different ways I can arrange the 3 people. So for that 60, I've actually created 6 times more groups than there actually are. Because I can take, for every group of 3, there are 3 factorial ways of arranging those 3 letters. So really, the correct answer is 60 groups divided by 3 factorial. Or really, there are only 10 different, we call it a combination. 10 different group combinations are possible for our answer. Let's look at Lotto 649. That's the Ontario lottery, probably one of the most famous ones. Now, the way you play Lotto 649 is you must choose 6 numbers between 1 to 49, and then 6 numbers are drawn at random, and to win the jackpot, you have to have the correct winning 6 numbers. The order that you select those numbers in does not matter. So, at first you might think of looking at a solution like this. There are 6 possible numbers I can pick. I have 49 choices for the first number, times 48 choices for the second, times 47 for the third, and so on. Now that is the same as calculating the number of permutations of length 6 from 49 possible numbers. However, which is the same as 49 factorial divided by 49 minus 6 factorial, 49 factorial divided by 43 factorial. That is a lot of numbers. It's massive. If you put that on a regular calculator, scientific calculator, you're probably going to find you're in scientific notation because the number is so large. Now, those at first might seem like the number of possible tickets. But notice I've said 49 choices for the first times 48 choices for the second and the third and so on. That assumes that there's some sort of important order to the numbers. Either they're written in order or they're drawn in a certain order. In fact, this calculation right here always assumes that there is an order that matters. A permutation is an arrangement. In this case, there is no proper order. Okay, if you pick the number, I mean, look at this ticket right here. You can kind of see those numbers there. It doesn't matter what order you pick those numbers in. Those are the 6 winning numbers. They're just written in numerical order. So there are clearly less tickets than this massive number. How many less? Well, once you have the 6 numbers, there are 6 factorial ways of arranging 6 numbers. So I've overcounted every single combination of numbers. I have 6 factorial times too many because I've considered all the possible arrangements as being another winning ticket when it's not. So we actually take this massive number, 49 factorial divided by 43 factorial, and we divide it by 6 factorial because it's too big. That actually ends up just looking like this. if you figure that out on your calculator, you find you get a much smaller number. It's still pretty big. A little less than 14 million possible tickets. All the examples we've been working on are called combinations. They're the number of ways you can select elements from a set where the order you select them in doesn't matter. So let's just revisit some of the examples, and I'll introduce some of the notation as well. So for the 4 of the 10 stuffed animals, there are 210 ways to choose those 4. We often refer to that as 10 choose 4. That's how we say it. And it actually has a notation. It looks like this. 10 over 4 with the brackets there. Another notation is the 10C4, like that, or 10C4. And not very common, C10, 4, like that. You probably have an NCR button on your calculator. And if you type in 10 NCR4, you will immediately get the answer of 210. If you have an NPR button, you almost certainly have an NCR button, and you can probably find it pretty easily. The next example, we had 5 students choosing 3 of them, so that's 5 choose 3. Okay, well, we got 10 possible groups, and that's because 5 choose 3 is equal to 10. In the Lotto 649 example, we had 49 numbers, and we had to choose 6 of them. So 49 choose 6 gives us that number a little less than 13 million. In general, we talk about N choose R. And the notation is like this, or NCR. Now, in general, how do we calculate N choose R? Besides using the button on our calculator, we can. But N choose R is equal to N factorial divided by N minus R factorial. And the reason that's true is, remember our Lotto 649 example? We took 49 factorial and we divided by 43 factorial because we wanted the number of permutations of length 6 from the 49 numbers. But then we said that we'd overcounted by 6 factorial. We'd counted too many because we counted the different arrangements of the number as if they were all different, and they're not. So here that means we'd also divide by R factorial as well. So N choose R is equal to N factorial divided by N minus R factorial divided by R factorial. Or you could say that N choose R is equal to the number of permutations of length R out of N elements divided by all the arrangements of those, R factorial, which gives you the exact same thing. It gives you N factorial divided by N minus R factorial divided by R factorial, which of course just simplifies to this right here. So when you get to an example like this, this is a very simple example of how to use combinations in math. A basketball team of 12 players will be selected from 25 students who try it. How many possible teams can be chosen? 25 choose 12. Now you can just use your calculator to get that answer. Okay, 25C12. And it's a very large number. 5,200,300. Now, if you don't have an NCR button on your calculator, there's a few options. One option is you could technically use this formula right here. You could just use the factorial button if you have that factorial button. So in this case, that would be 25 factorial divided by 12 factorial divided by 13 factorial. Or you could Google a combination calculator. I Googled combination calculator and I got this N choose R calculator. So it allows you to do that as well. So feel free to use that. For the next question, Mr. Elliott has 40 possible questions to put in a math test. He must select 10 of these questions to use in the test. How many possible tests could he create? Well, 40 choose 10. How many ways can I choose 10 tests. 40 choose 10, and that is a massive number. 847 million. Now, there's a big assumption in this question about how many possible tests could I create. That assumption is that the order of the questions doesn't matter. So the same 10 questions in different order doesn't count as a new test. I don't know if that's a fair assumption or not. If we did say that the order of the question matters, then you'd be talking about P, NPR, 40, P10, which would be a lot larger than that already massive number. Suppose we were to look at some simple NCR or N-choose-R calculations. Some of these we should actually be able to do without a calculator because this should make sense. N-choose-1. How many ways can you choose one element out of a set of 9? Well, that's 9. This is basically saying there are 9 people. How many ways can you choose one person? Well, you could choose each person, so 9. 9 choose 9. If you have a set of 9 people and you need to choose all 9 of them, there's only one way to do that. How about 10 choose 9? So this basically says I have 10 people and I need to know how many ways can I select 9 of them. That might seem complicated at first, but look at the other way around. Imagine you want to know how many groups of 9 can I make out of 10 people. Well, that's the same as saying how many ways can I select the one person who's not included in the group? Since there's 10 people, there's 10 different groups. This is actually the same as 10 choose 1. 5 choose 0. This is defined as 1. Okay, there's only one way to choose no one out of a group of 5, and that's the null set, which gives you an answer of 1. Explain why 49 choose 3 is the same as 49 choose 6, pardon me, is the same as 49 choose 43. Well, this gets back to the Lotto 649 example. Instead of picking the 6 winning numbers, you could also look at the problem being pick the 43 losing numbers. So technically, Lotto 649 is the same as Lotto 4349. Imagine trying to pick 43 winning numbers. That would be the exact same thing as picking 6 winning numbers. I don't think that people would see it that way, but it's true. So, I mean, my answer to this, if you're going to write something out, you can choose 6 of 49, or you can choose the 43 that are not in the 6. That's how I would describe that. How about if we want to consider the possible student councils we could have? So in a certain school, a student council consists of 1 president, 2 vice presidents, 2 sports reps, and a treasurer. And we are told that 3 students run for president. Well, let's start with presidents. If there's only 1 president and 3 students run for president, we have 3 possible presidents. We could also look at that as 3 choose 1, which is also equal to 3. It doesn't matter. How about vice presidents? There are 2 vice presidents and 6 students run for vice president. So we have 6 students and 2 of them will be chosen for vice president. So there's 6 choose 2 vice presidents. By the way, we're assuming that no one who ran for president also ran for vice president or something like that. Now we're actually going to multiply these possibilities together. And when I multiply them together, I get all the possibilities for my presidents and vice presidents. Because for each 3 of the possible presidents I could have, there are all of these possible vice presidents to go with them. We also have 10 running for sports reps, and there are 2 sports reps, so we multiply that by all the possible sports representative groups we could have. And then 2 for treasurer, so we have 2 possibilities for treasurer, or 2 choose 1. This gives us 3 times 15 times 45 times 2, or 4,050 possible different student councils. In this next example, we have a class that consists of 19 students, and we want to choose 6 students at random to complete a survey. So how many groups of 6 can we form? Well, 19 choose 6. Which on my calculator, 27,132 possible different groups of 6 people from the class of 19. Now we get into probability. What's the probability that only females will be selected for the survey? Well, our total outcomes is that 19 choose 6. There are 27,000 outcomes. How many of those outcomes are all female? Is that a possibility? That is a possibility that all 6 of them could be females. And the way we can answer this question using combinations, we can just say, imagine we had written out all of the possible 6 student groups, all 27,000 of them, this huge list. And we want to count how many of those would just have females in them. Well, there are 12 females in the class. So how many ways can you do 12 choose 6? That's the number of ways we can select 6 females from out of 12. So imagine if maybe the groups were written, the 27,000 different groups, we had all the names of each 6 of them written out. Okay, 12 choose 6 would be the number of names written out where there just are females in the class. If you figure that out, you get there are 924 divided by 27,132, and that's about 3.4% if you divide those numbers, multiply by 100. How many groups of 6 can be created if exactly 3 males and 3 females are required? Well, the way I would tackle this one is I would just look and say, okay, well, let's start with the number of males that could be selected. There are 7 males. We need to choose 3 of them. And that gives me all the possible. So it's almost like I'm treating it as, instead of 1 group of 6, 2 groups of 3. So those are the possible males. Multiply that by the possible females. Just like that. And that's 35 times 220. So what you're doing here is you're basically saying, look, there are 35 ways to select 3 males. For each of those groups, there's another 220 groups of females. So 35 times 220 gives you all the possible groups we could have. You don't need to know anything about poker to look at this question, but basically the one thing you do know is you have 5 cards in poker. Okay, so let's just say this is a simple game of poker where you're just given 5 cards at random. So how many possible hands are there in poker? There are 52 cards in a deck. So 52 choose 5 is the number of possible sets of cards you could have. The order you get the cards in, of course, doesn't matter. That's about 2.5 million different hands. Now, what's the probability that all 5 cards have the same suit? That's called a flush. All hearts, all diamonds, or so on. This is probably one of the more difficult questions in this lesson. Let's just start with the idea that they're all, say, all hearts, for example. There are 13 hearts in the deck. There are 13 choose 5 ways to select 5 hearts out of the deck of cards. Okay, so you're choosing 5 of the cards for your hand out of 13. Divide that by all the possible outcomes. 52 choose 5. Now, we don't just care about all hearts. We care about all diamonds, all clubs, all spades. It could be any suit. So there's actually 4 different suits. So really, the 13 choose 5 is just all of the hearts. But there's the same number of all diamonds hands and the same number of all clubs hands. So we multiply that by 4. Sometimes you'll see people write 4 choose 1 here, as in choose a suit, and then multiply that by all the ways there are to select 5 cards from that suit. If you figure that out, you get, I think, 5,148 divided by our large number of 52 choose 5. That probability is actually a little less than 0.2%. So if you divide that, multiply by 100, you don't even get to 0.2. We're going to revisit that question in a second. But first, let's talk about the royal flush. So a royal flush is 10, jack, queen, king, ace, all of the same suit. So what's the probability of being dealt a royal flush on 5 cards? Well, there are 52 choose 5 possible outcomes of getting 5 cards. How many of those are royal flushes? This is actually a simpler question. You can either have the 10, jack, queen, king, ace of hearts, diamonds, spades, or clubs. So there's only 4 royal flushes in the entire deck. Well, 4 divided by 2.5 million, okay, it actually gives you 1 out of 649,740, okay, that's 4 over that 2.5 million number. They both divide by 4, which gives you that. So a little better than 1 in a million, but getting close to 1 in a million chance of getting dealt a royal flush. which is an interesting question in statistics, because then the question becomes, what's the higher probability that your opponent got dealt a royal flush or that they cheated? Let's go back to that other question about how being dealt all 5 cards of the same suit, because this sounds like something we've seen before, and it actually is. We could answer this question without needing to use counting methods. I call combinations and permutations counting methods. So the other way to do this would be to look at these as events, so to speak. So what is the probability you get 4 hearts in a row? Well, the probability that the first card dealt to you being a heart is 1 out of 4. And I multiply that by the probability the second card is a heart. Well, the probability the second card of a heart goes down. These are not independent events. Now there are 51 cards left in the deck, and only 12 of them are hearts. Multiply that by the probability that your third card is a heart. There are 50 cards left in the deck. Only 11 of them are hearts now. The fourth card, there are only 10 left out of 49. And finally, the last one, also being heart, is now 9 out of 48, because there are 48 cards left in the deck and 9 of them are hearts. If you multiply all of that together, you end up getting 47,520 divided by that right there, which is exactly the same as our answer before, also a little less than 0.2%. So both methods work here. In one method, I'm using combinations. In this method in blue, it's almost like what I'm doing is I'm thinking about all the ways I could write down possible 5-card hands. 52, choose 5. And then I'm saying, what are all the possible ways I could write down 5-card hands where all the suits are the same? And in this next example, which I've actually made a mistake and I'll fix it right now, I figured out the probability of all hearts by getting a card as an event. Okay, a quarter of a time you'll get a heart on the first card, times 12 out of 51 on the second, and so on. And using independent, well, these are not independent events, but thinking about events and probabilities instead. And the mistake I made here that I'll fix right now, sorry, is that I have to multiply by 4, because it could be of any suit. So multiply by 4 here, and that's actually when you get this correct answer here, since there are 4 different suits. So again, you're welcome to do either. When it comes to probability, you can take either approach, and in this case, it's up to you to decide which one's easier. Okay, bye for now.